All right, so now that we know two ways to locate a point on a plane, we might as well learn another. Polar coordinates are very similar to vector coordinates, except they have some particularly special characteristics. First of all, we only care about the positive x-axis. In fact, it's not even called the positive x-axis when we talk about polar coordinates. We call it the polar axis. And the origin, we don't call the origin because we're not dealing with a Cartesian plane. We call the origin the pole. So then in order to locate some point, let's call it P, we would locate it based on its angle from the polar axis and the radius or the distance from the pole to the point along the terminal ray. And like Cartesian coordinates, they have an ordered pair, and the pair is to give the magnitude or the length from the pole to the point and the angle theta. For example, let's find the point polar coordinate, the polar point, r equals 1, theta equals 200 degrees. Now, in a perfect world, I'd be able to sketch in the pole and I'd have a protractor or maybe some graph paper that would make this easier. And check it out, polar graph paper. So I erred on the side of leaving as much space as possible to work, and so it's not so easy to see these markings around the edge, but the pole right here, the polar axis, the pole would be the center and the polar axis would be right here. And on the inside, we have degree measurements, 15, 30, 45, and so on. And on the outside, we have radian measurements for the same dimension angles or the same sized angles. So if I wanted to plot the point 1, 200, the first thing I want to do is find where would 200 be? Where would the terminal side of 200 be? And I could find that using the polar graph paper. So if I start here at the polar axis and work my way around, I see that right here is 195 and right here is 210, which means 195, 200, 205, and 210. So right here would be the 200 degree angle that I want. Now all I have to do is figure out where on that 200 degree angle terminal ray, that was a lot to say, wasn't it? Where on that terminal ray would the value, measure value of 1 be? And I'm going to label over here on my polar axis exactly as I would on a Cartesian axis. I'm going to call each of these intervals 1/2 of a point. So this would be 0.5 or 1/2. This would be 1, 0.5, 2, 0.5, 3, 0.5, and out here would be 4. So if I follow the 1 all the way around, that would be my distance from the pole to my point equal to 1. And we don't draw this, that's part of the lesson. So you would just plot the point. You could label the point as 1, 200, or you could just rest on the fact that you have graphed the line, the terminal ray, and that you've labeled your polar axis. And trust me to follow around and see what you're thinking. All right, so let's do another example, and I want to use the same polar grid. This time I'm going to plot point R, and it has polar coordinates -2 and 3 pi over 2. So this time we have our angle in radians, no big deal, and we have our measure is a negative value. So what impact will that have on the actual graph? Well, let's start with our radians. So if I start with a ray on the polar axis and take it around to 3 pi over 2, I end up here. And so you might think at this stage that, well, then all I have to do is plot the point 2 on that ray and I'm done. But I can't do that. This point represents 2, and I don't have a -2 over here. If I did, it would make -2 and +2 exactly the same location. That would never fly. And so a negative radius means exactly the same thing as negative always means. It just means in the opposite direction. And so I'm going to take my ray, I'm going to turn it exactly opposite. And now I can plot on 2 because this represents the point -2 or the opposite of 2 on, by default, the opposite of 3 pi over 2. So that's plotting points on a polar graph, but we can also plot equations on a polar graph. And I'm going to show these through example. So example 3, or another example, let's find or plot the equation r equals 2.5. So what are we talking about when we say r equals 2.5? Well, just like any equation, we're talking about all the points, making a graph of all the points for which that is true. And all of the points for which 2.5 is true would be 0.51, 0.52, 0.53, 0.54. I have my labels here. So 2.5, certainly this point would work on the polar axis, 2.5, but so would every point on this circle at 2.5. So trying to be as neat as possible, this would be the graph, the polar graph of the circle with a radius of 2.5. Similarly, we can graph just the angle. So for example, if we were asked to graph theta equals 5 pi over 6. Well, we're asking for which points, list all the points, would theta equal 5 pi over 6. So if we go to 5 pi over 6, which, let's see, if this is 6 pi over 6, this would be 5 pi over 6. So my terminal arm or my terminal ray would be there. Now, it's also true, though, I want to know all the points that are on the angle or the terminal ray 5 pi over 6. We're also looking for negative points, which means we're also looking for opposite points for 5 pi over 6. So this would be the graph of the angle 5 pi over 6, where some of the points would be negative and some would be positive. And you could draw a few in just to show that it's all of these points. But like any line, we're talking about all the points on that line. So the last introductory part of dealing with polar coordinates is looking at the distance formula for polar coordinates. So this would be the distance between 2 points on a polar plane would be the formula r1 squared plus r2 squared minus 2 times r1 r2 times the cosine, this is looking familiar, isn't it? It's almost exactly the same, times the cosine of theta 2 minus theta 1. So almost the law of cosines, but more importantly, we're asking, what does this describe? So if I have 2 points on a polar plane that don't necessarily fall in standard position, just any 2 points, say this point and this point, well, I could call this point P1, and that would be R1 theta 1. And if this point were P2, the coordinates would be R2 theta 2. Maybe orange wasn't the best color to use here, but we're not going to do any work with it. We're just going to use it to visualize. So there, if I'm looking at the length of the line between these 2 points, P1 and P2, each having their own polar address. All I have to do is plug in the values, pluggy chuggy, done. So let's do one example of that and call it a day. This is a word problem, so I'm going to read it. An air traffic controller is tracking two airplanes that are flying at the same altitude in miles per hour. The coordinates of the planes are, and I'll give those in just a moment, and we want to first sketch the graph and then determine how far apart they are. So first I need another polar plane or polar grid, and then I need a pair of spyglasses to figure out where the heck these angles are. But let's start by writing them down. So airplane A is at the coordinates 8, 60 degrees. And airplane B is at the coordinates 4, 300 degrees. All right, so when we plot these, we're not going to sketch in the ray. We're just going to find the location on the plane. So first, 8, 60 degrees, I'm going to have to decide my units here. And I think 1, 2, 3, 4, 5, 6, 7, 8, that fits perfectly. And so all I have to do is find out where 60 degrees is, and I'll know where to plot my 8. And 60 degrees is right there. So that's point A at 8, 60 degrees. Point B is at 4, so it's going to be on this inner circle right here, 300 degrees. And 300 degrees, holy moly, is somewhere down here. So 180, 270, 300, right there. So 300 degrees on the 4 magnitude line, or the 4 radius. Okay, so these are the 2 points we're going to work with. And now we just want to find the distance between them. How far apart are the 2 airplanes? So the distance then is just the formula, pluggy chuggy. So let's call A point 1, and let's call B point 2, just so we have designation values to put into the formula. So radius 1 is 8 squared, plus radius 2 is 4 squared, minus 2 times 8 times 4, so that's 2 times 32, times the cosine of theta 2, 300, take away 60. All right, so let's just chunk this down a little bit. Square root 64 plus 16 minus 64 times the cosine of 300 take away 60 is 240. So I'm going to have to pull out my calculator, I think. 64 and 16 is 7480. That'd be 80 minus 64 times the cosine of 240. That definitely needs a calculator. Make sure I'm in degrees, and I am. So the cosine of 240, and I want that in a decimal value, is negative 0.5 times 64 is negative 32. So negative 32. So I've got 80 plus 32, 112. I'm going to do that just all together just to be sure. So the square root of 80 plus 32 is 10.583, or approximately 10.5 miles. So approximately 10.5 miles. And that's it. Pluggy chuggy math when it comes to calculating the distance using the logic that we already have. It shouldn't be a giant leap to be able to plot polar coordinates on a polar graph or polar graph paper.